Hi everyone. Here you are going to learn about the encoding or the generation of non-systematic cyclic codes. Okay. Here in the last video you learned about the how to create the generator polynomial and the generator matrix of both non-systematic as well as systematic cyclic code. Okay, so here you are actually going to learn how to create the cyclic code itself. Okay, you are going to create the non-systematic cyclic code, right? So this circuit, right, the main thing about the circuit is that it uses the multiplication circuit, or we also call it as the multiplier circuit. Okay, so because the reason why we are using the circuit is because we all know the equation of the output code word, or you all know how to create a cyclic code word, right? We all know how to create cyclic code. We use this is v of x represents the non-systematic cyclic code, and this v of x is equal to u of x into g of x. You see, so basically this is actually a multiplication of two polynomials, and that is exactly what we are going to do here. That is why we need a multiplication circuit. In the last video, in the previous video, you actually learned how to create the generator matrix or the generator polynomial and the generator matrix of both systematic and non-systematic cyclic code. Here you are going to learn how to generate or how to create or how to encode this, or how to create the v of x, that is the non-systematic cyclic code. This is what you're going to learn in this video, and the circuit we're using for that is called as the multiplication circuit. Okay, so therefore before we are going to this actual circuit, first I need to tell you the working of the multiplication circuit. Okay, and it's a very simple, the circuit is extremely simple. All you need to understand is some of the basics of how we are going to implement this. So first, to do that, first what I'm going to do is I'm going to assume two random polynomials. Okay, let me say a of x and b of x. So in that case, a of x, okay, I'm going to assume that a of x is equal to a0 plus a1 x plus a2x square plus it's a2, okay, a2x square plus a3x cube. Okay, remember that this a0, a1, a2, a3 are nothing but binary values. Binary values means these coefficients can either be 0 or 1, no other number, either 0 or 1. If it is 0, then that corresponding term will be missing. If it is 1, then that corresponding term will be present. So when I say 1 plus x cube, when I say 1 plus x cube, then a0 is 1, a1 is 1, a2 is 0. That's why there is no x square inside that polynomial. So a2 is 0 and a3 is 1. That's why when I say 1 plus x cube, I actually meant 1, 1, 0, 1. Or in other words, we can express it like this. That is, a is equal to a0, a1, a2, a3. Okay, this is how we represent it. Then the matrix form is like this, the polynomial form is like this. Same way, let me take another polynomial, let me call it as b of x, and therefore b of x I'm going to represent as b0 plus b1x plus b2x square plus b3x cube. Okay, and when I'm going to represent in terms of matrix, it will become, let me put a bracket over here just to show it is a set. Okay, a curly bracket, and this is b0, b1, b2, b3, and there you have it. This is the matrix of b. Okay, this is how you represent the matrix, this is how you represent this polynomial. Okay, but the reason why I'm writing like this is because you need to understand this is how you represent. Okay, but now I'm going to talk about the actual working of the circuit. When you go to the actual working of the circuit, right, we need to know that this is the higher order coefficient, this is the lower order coefficient. Or another way of saying is that this is the first thing that you are going to transmit. A3 or B3. A3 is the first message you are going, is the first bit you are going to transmit. A2 is the second bit. A1 is the third bit, and A0 is the fourth. That's how the actual working actually comes into the picture. That is, we would first transmit the higher order coefficients, and then correspondingly you go to the next coefficient and you transmit the next coefficient that comes after that, and so on. This is how the actual working is. So even though, just don't get confused, even though we express the matrix in this form, both the polynomial as well as the matrix, we write it in this format. Even though we write it in this form, the first bit that you're going to transmit will be the the highest order coefficient. Always we transmit this operation. So when I'm going to explain this operation, I'm going to explain in such a way that this is the, I will transmit, or the first input bit will be A3. Okay, the reason why is because you see, when we speak of a number, for example, if I take a number 532, so here 5 is the most significant digit, 2 is the least significant digit. Like that, over here also, here A3 is the most significant bit and A0 is the least significant bit, which means if you are going to do multiplication, you are going to do the multiplication like this, that is A3, A2, A1, A0 into B3, B2, B1, B0. Okay, this is how we generally write the multiplication operation. So we all know what is this multiplication operation is, right? So how to do the multiplication operation is, first I will multiply B0 with all these, with the first, with A of x. So I will get A0, B0. Here I will get A1, B1. Sorry, A1, B0. Here I will get A2, B0. Here I will get A3, B0. Next I'm going to multiply with B1. So it will be, so I'm going to shift 1 to the right and I will get A0, B1, A1, B1, A2, B1 and A3, B1. Next is, again I'm going to shift to the right and multiply this with B2 and I will get A0, B2, A1, B2, A3, A2, B2, and then you will have A3, B2. And then again I'm going to shift again to the right and I'm going to multiply with B3 and I will get A0, B3, A1, B3, A2, B3, and last it will be A3, B3. Okay, this is how we do the operation, the entire operation. And then what you will do is you add everything. And let me tell you again and again, I'm telling you, when I'm talking about addition, I meant nothing but XOR operation, nothing but pure XOR operation. This is not even your usual half adder or full adder. That is not the kind of multiplication we are explaining that we are going to use for this. Okay, because here you, like I said, whatever you do, you should either get whatever operation you are going to do, you should either get 0 or 1, nothing else. Just only one, whatever operation you do, the output is only 1 bit. The output should be only 1 bit. So you cannot, no, this is nothing to do with your half adder or full adder. This is normal, nothing but your XOR operation. So this is A0, B0 plus 0 plus 0 plus 0 is nothing but A0, B0. That is your least coefficient, coefficient, right? Or the coefficient of the lowest order. And here you, next to, after that you will add these two and you will get A1, B0 plus A0, B1. Here when you add all of them, you will get A2, B0 XOR. When I say plus, it's XOR. A1, B1 plus A0, B2. Over here also, when I add all of them, I will get A3, B0, A2, B1, A1, B2, A0, B3. It's nothing but XOR of all of them. Okay, it's the XOR of all of them. Over here also same thing. A3, B1 plus A2, B2 plus A1, B3, and next, and I will add these two and I will get A3, B2 plus A2, B3, and then I will add this only A3, B3 is there, so that will be the only term left, A3, B3. So when you write this coefficient, this is the highest order, this is the lowest order. Okay, so when you're going to write, we start writing from here. When you're going to express this in polynomial form, we start writing from here. When you're going to express it as a matrix also, you start writing from here. But when you're going to express it as a number, you start writing from here, because this is the most significant bit and this is the least significant bit. Okay, and like I said, another interesting thing about this is there is no carry over here. You will never find a carry over here, because like I told you, this is nothing but pure XOR operation. There is no half adder operation or full adder operation over here. Pure XOR operation. Nothing but only XOR operation, which means there won't be any carry also. Which means, that means if you start adding from here, if you start adding from here or if you start adding from here, both of them, you will get the same answer. That's another interesting aspect about this. Okay, so now how to draw the multiplication circuit. Okay, so to draw the multiplication circuit, you need to understand that this circuit is designed by looking at the values of the multiplier. Multiplier means, like I told you, so suppose if I say 5 into 3 is equal to 15. So 5 is called as the multiplicand, 3 is called as the multiplier, 15 is called as the product. The same way, when I say that C of x is equal to A of x into B of x. Okay, when I say C of x is equal to A of x into B of x, C of x is called as the product, A of x is called as the multiplicand, and B of x is called as the multiplier. And we design the circuit based on the value of the multiplier, or based on the value of the second polynomial, that is B of x. That is how we usually start this. Okay, so this is how we usually do all this. That is, we usually look at the value of the multiplier. All you need to do is simply look at the value of the multiplier. That's all. Simply look at the value of the multiplier. So here, how to draw is, first I will look at the polynomial. So like I said, this is the polynomial, right? This is exactly the polynomial, and then what you do is you simply look at the degree of the polynomial. The degree of the polynomial is equal to the number of shift registers that you need to use. As if you look over here, it's being shifted 3 times, right? One time it's being shifted to the right, other time shifted again, other time is shifted again. So which means basically you need 3 shift registers, or you simply look at the degree of the polynomial and you create the number that many times of shift registers. So first let me draw the shift registers. This is first shift register, this is the second shift register, and this is the third shift register. Okay, this is the third shift register. Then let me connect all of them together also. Okay, this is SR1, this is SR2, this is SR3. Okay, shift register 1, 2, 3. 3 shift registers because the polynomial degree is 3. That's why. Okay. Now next what I'm going to do is that at the output of every shift register, I'm going to put an XOR function. At the output of every shift register. That's it. That's it. But before drawing the output, let me draw the switch. Okay. Then the value of the switch depends on the multiplier. I will tell you what is the meaning of the switch. This is just a normal switch. Okay. The reason why I'm calling a switch is because I don't have any other name for it. There. Okay, and I will tell you the meaning of these switches later. Okay, this switch is called as B3. The same B3 over here. The same B3. Okay, the same B3 over here. Okay. This switch represents the switch for B2. This switch represents the switch for B1. This switch represents the switch for B0. And then after the switch, I will draw the XOR function, or the XOR gate. Here you don't have to draw the XOR function because here only one single input is available. So just simply join that over here. Okay. And the output of this will go over here, and this will go over here. There. So like I told you that the circuit depends, the implementation of the circuit depends only on the values of the multiplier polynomial. That is the interesting thing about this. Okay, so this is actually so what you are thinking is actually correct. That is, this is not your normal multiplication circuit. This is simply a multiplication with their second number. That is, this is nothing but a circuit in which you can multiply any number with b of x. That kind of circuit is what you are being designed here. That is, one input is actually fixed. That is the second. That is that input is the multiplier. That input is fixed. The other input is the one you are going to transmit. The reason why you are making this is like this is because that's exactly what we are actually doing over here. You see here, g of x is the generated polynomial, and this is value is fixed. This is depends on which message you are going to transmit. that polynomial changes. So this is a fixed value. This value usually changes, right? And corresponding that we will get, that's why it's called as the encoder, because this will be encoded into this, right? So that is why we are drawing a circuit in which one input is fixed and the other input is your multiplicand. So you will send A of x into the circuit, and over here you will get C of x. This is the working of the circuit. And like I said, if you want to understand the working of the circuit is very easy to understand. It is like I told you that we all know that the value of A of x is this value over here, right? I'm not going to write it again. A0 plus A1x plus A2x square plus A3x cube. And the first, and always you will transmit, or you will always insert the first bit of the highest order coefficient. Always we will transmit, or we will send into the circuit the first order coefficient, and then correspondingly we will go for the next and the next and the next. So the first value you are going to insert is A3, then after that you will transmit A2, after that you will transmit A1, and then you will transmit A0. So the first value you will transmit is A3. So now look what will happen when you transmit A3 over here. When you transmit A3 over here, what will happen is then A3 will be multiplied with B3. So you will get A3 B3, and here no values are over here because all the values of shift registers are reset to 1 or reset to 0, right? They are all in reset mode. No input has ever been shifted. So at the starting state, so all these values will be 0. So you will get A3 B3 plus 0 plus 0 plus 0 plus 0 plus 0. Therefore, C of x is nothing but A3 B3, which means this value. This is the first value you will get from the output. That is, you will get the output of the highest order coefficient first. That is the main thing you need to understand. Okay. Then what will happen? The next cycle, or on the next shift cycle, what will happen is that A3 will be shifted over here, and A2 will be shifted next into the circuit. So then what will be your circuit? Then the value over here will become A3, and then the value over here becomes A2. So in that case, what will be your output? Your output value will then become A3 B2 plus A2 B3. Here, because here you will get A2 B3, and here you will get A3 B2 plus 0 plus 0 plus 0 plus 0. Therefore, you will get the second coefficient, the second highest order coefficient. That is A3 B2 plus A2 B3. And then what will happen is that again at the next shift cycle, this A3 will be shifted over here. So this will become A3. A2 will be shifted over here. So therefore this will become A2, and your next input will become A1. So what will be your next input? Your next input will become A3. So here it will be A3, here it will be A2, here it will be A1. So you will get the input will become A1 B3 plus A2 B2 plus A3 B1, which is nothing but this coefficient. Then what will happen? Again A3 as usual, again A3 will be shifted over here, and then A2 will be shifted over here, then A1 will be shifted over here, and then next value shifted over here will become A0. That means here the value becomes A3, here the value becomes A2, here the value becomes A1, here the value becomes A0. So therefore you will get, the next value you will get is A0 B3 plus A1 B2 plus A2 B1 plus A3 B0, which is nothing but this value over here. You see how the working is done? The working is just like that. You see, now what happens is that now A3 will be discarded, right? After the cycle, the A3 will be discarded. It has nowhere else to go. And then what happens? A2 will be shifted over here, right? A2 will be shifted over here. A1 will be shifted over here, and A0 will be shifted over here. And here there is no other input to shift, so you will be shifting 0 inside. The reason why you are shifting 0 is because after transmitting all the input, then what you need to do is also required that the shift register still contains some more answers. So in order to flush those answers out, you will be transmitting zeros into it. So since there are 3 shift registers, you will be transmitting 3 zeros. After you are transmitting your input, you will transmit 3 zeros in order to get the remaining answers from the shift registers. So in that case, so here you will get, so here it will become A2, here it will become A1, here it will become A0, and here it becomes 0, right? Here it will become 0. So the answer you will get is A2 B0 plus A1 B2 plus A0 B2 plus 0. Here it is 0, right? So you will get only these 3 answers. That is A2 B0, A1 B1, and A0 B2, which is exactly the answer that you'll get over here, right? This is the coefficient you'll get. Then what happens is that A1 will be shifted over here, A0 will be shifted over here, and then 0 will be shifted over here, and then another 0 will be put at the input, will be placed at the input. So what happens is here it will become A1, here it is A0, here it is 0, and here it is 0. So what you will get A1 B0 plus, here you will get A1 B0, and here you will get A0 B1. So therefore you will get A1 B0 plus A0 B1, which is the value over here. And then what happens is that this A0 will be shifted over here, this 0 will be shifted over here, this 0 will be shifted over here, and another 0 will be placed at the input. Okay, so what will happen now? What will happen is that now what will happen over here is that this A0 will be multiplied with B0, and you will get A0 B0. This is how the working is done. So first, when you look at this, you will transmit the highest, the polynomial of the highest order coefficient. Okay, the coefficient of the highest order, then you will transmit the coefficient of the second highest order, then you will transmit the coefficient of the third highest order, like that it goes on, and finally you will transmit the last bit you will be transmitting will be A0. After transmitting A0, in order to flush all these shift registers, you will be transmitting extra zeros in order to flush out the remaining answers from the shift register. This is the actual working of the multiplication circuit of 4-bit. Okay, so here now let me draw the general block diagram. This is the general circuit diagram. Okay, general circuit diagram of your multiplication circuit, and here you are going to assume that that both A and B are of m bits. M bits means the degree of polynomial becomes m minus 1. So this is how it's being expressed. That is A0 plus A1 x plus a2 x square plus up to a m minus 1 x raised to m minus 1. Likewise, b of x is equal to b0 plus b1x plus b2 x square plus up to bm minus 1 x raised to m minus 1. And this is how we represent it. Okay, like I said, we'll start with the highest order or coefficient. We will first transmit the highest order coefficient, and then correspondingly second highest order coefficient, third highest coefficient, and so on. And again, the circuit is designed based on the values of the multiplier alone. Okay, so this is not actually a of x into b of x. This is actually any input into b of x kind of a circuit. That is what you need to understand. Now, another thing is that, like I said, this is called as a switch. The reason why I'm calling this a switch is because, like I told you, this is actually this over here. Okay, this is actually nothing but this value of this, like I told you, this coefficients are nothing but 0 and 1, right? They are all nothing but binary values. So which means if it is a 0, the switch is open. Switch open means what? That arrow mark, you don't even have to draw the arrow mark. That arrow mark itself will be missing. That arrow mark will be open, or the arrow mark will be absent. That's what it means. Okay, and when I say when b0 is equal to, when I say that coefficient is equal to 1, it means that arrow mark is present or it's being shortened. That's all. That's all that it means. That is, if the coefficient is 0, if the coefficient is 0, then that arrow mark you don't have to draw that arrow mark. You don't have to draw that arrow mark. And if the coefficient is equal to 1, you just simply need to short it up. That's all. Just simply short it. Okay. This is how we express it. That's the meaning of this. So, like for example, okay, when I say that b of x, okay, let me take b of x, and when I say b of x is equal to 1 plus x square plus x cube, when I say b of x is equal to 1 plus x square plus x cube, so what it means is that the value of b0 is 1, the value of b1 is 0. The value of b1 is 0. Why? Because x is missing from here. So therefore the value of b1 is 0. The value of b2 is 1 because x square is present. And the value of b3 is also 1 because x cube is also present. So when I'm going to draw the circuit, this is b3, this is present, this is also present, this is missing. So you don't have to draw this arrow mark at all. This will be shorted. This will be shorted. This is also be shorted. You don't have to draw the switch also. And this is also will be shorted. So that will be the circuit. This arrow mark will be missing. Rest of them will be there. That is what I meant. That's why when I call it as a switch. That is, if it is 0, the switch is open. If it is 1, the switch will be closed. So that is how we are going to implement. Now I have explained to you the actual circuit. So now drawing the circuit will become very easy for you. Okay. it become very easy. So likewise, like I said, v of x, let me write that v of x is equal to u of x into g of x, right? So in the previous video, right, if you remember in the previous video for non-systematic cyclic code, the value of g of x that I have chosen was actually 1 plus x cube, right? In when we discussed about how to create the generator matrix or the generator polynomial and all that, I told you that the generator polynomial which I chosen for a 7-4 cyclic code was 1 plus x cube. So what I'm going to do is that this is 1 plus x cube. Okay, now next is I need to choose some value of the input. So let me choose the value of input as input is equal to what value should I choose? 1 plus x square plus x cube. Okay, let u of x is equal to 1 plus x square plus x cube, or in other words I'm going to say u is equal to 1101. Okay, sorry, it is 1011. Sorry, it's 1011. U is equal to 1011. The reason is because this bit represents the last bit, and this bit this represents the highest order bit. This represents x square. There is no x, so therefore u is equal to 0, and there is x is equal to 0 is the first bit, and there's 1. That's why it's written as 1011. But when you are going to draw a circuit, you will first send this one, then you will send this one, then you will send this 0, then you will send this one. Okay, that's how you draw. So this is the value of u, and this is the value of u of x. Okay, so what will happen if I multiply u of x with g of x? What will I get? Let me see. That is v of x is equal to u of x into g of x, right? Or in other words, what is u of x? 1 plus x square plus x cube. And what is g of x? 1 plus x cube. Okay, so here when I'm multiplying it, what will I get? First I will multiply 1 with this polynomial, and I will get 1 plus x cube, plus then I will multiply x square with this polynomial, and I will get x square plus x cube plus x raised to 5, plus then I will multiply this x cube with this polynomial, and I will get x cube plus x raised to 4 plus x raised to 6. Okay, so I will get a polynomial of degree 6. It is basic understanding, because 3, so 3 plus 3 is 6. So therefore you will get a polynomial of degree 6. Okay, and so this is 6. So therefore how you represent the polynomial or this matrix of this code? 1 is present, x is present. Oh, x cube will be cancelled, because this x cube and this x cube will be cancelled. So these two will be cancelled. So 1 is there, x is there, x square is there. Yes, x square is there, so that one is also present. X cube already there's another x cube over here, right? So that x cube will be 1, and then there is x raised to 4 is there. There's no other x raised to 4, so 1. X raised to 5 is here, that is 1. X raised to 6 is there, that is also 1. So therefore this is the code you will get. You will get all ones. If you multiply 1011 with 1101, you will get this number. You will get this value right here. Okay, and this is the, remember, this is the coefficient of x raised to 6. This is the coefficient of x raised to 5. This is the coefficient of x raised to 4. This is the coefficient of x raised to 3. This is the coefficient of x square. This is the coefficient of x, and this is the coefficient of x raised to 0. Okay, so this is how we represent the matrix. This is how we represent the polynomial. Now let me show you the actual circuit. Okay, so to draw the actual circuit, like I told you, we will look at the value of the generator polynomial. That is all. All you have to do is simply look at the value of the polynomial. So drawing the encoder is actually very easy. Okay, simply look at, this is my multiplier. Okay, so we are going to create a circuit which is going to with which, if you can multiply any input with that multiplier, you will get the output. So the multiplier basically, or this value basically, will be constant. So this is how I'm going to draw. First I look at the degree. Degree is how much? 3. So I'm going to draw 3 shift registers. 1, 2, 3. Okay, I draw 3 shift registers, and then I will draw the input of all of them. I will connect all of them over here like this. Okay, and then I'm going to draw the switch. Now how will I draw the switch if you ask me? That depends on the value of the coefficient. So first over here, this will be the value of G3. This is the coefficient of G2, G1, G0. What is the value of G3? What's the value of G3? The coefficient of x raised to 3 is 1. So therefore the value of G3 is also 1, right? Or therefore that means the switch is present. That's what it means. So therefore I'm going to draw a line like this to show that there is a connection. This line represents nothing but the coefficient of this x raised to 3. This represents if I draw the space over here represents the coefficient of x raised to 2. Here the coefficient of x raised of x, and here the coefficient of x raised to 0. So if you look over here, there is now x square, which means the value of G2 is 0, which means you don't have to draw anything over here because the switch is open, like I said. So you don't have to draw over here, and here the value of x raised to 1 is, the coefficient of x raised to 1 is 1. So therefore I will draw a line over here, and here the coefficient of x raised to 0 is also 1. So therefore I will draw a line over here. You see, 1 plus x cube, or 1 into x raised to 0 plus 1 into x plus 0 into x square plus 1 into x cube. That is how we draw a circuit. And at the end of every line you draw the XOR function. Here no need to draw XOR function because only one input is there, right? So therefore this is it. This is the actual circuit. Okay, here you will transmit your input, that is u of x, and here you will get your non-systematic cyclic code v of x. This is SR1, this is SR2, this is SR3. Okay, so you see, this line represents the coefficient of x raised to 3. This absence of this line represents the coefficient of x square, because here this is actually 0x square plus 0x square. That is why there is no x square over here. That's why this over here is absent. And here this line is present, which means this represents this arrow mark, no, this signal or this line represents the coefficient of x raised to 1, and this line represents the coefficient of x raised to 0, or this one over here. This is the actual. See, so drawing a circuit is very easy. Simply look at the multiplier and just simply draw a circuit. Now I want to prove to you if the answer that I'm going to draw here is right or wrong. All right. So I'm going to explain to you the steps of this operation. So to explain to you the steps of the operation is also very easy. Or the best way to explain is by drawing a table. Okay. So let me first draw a table. So the first table is how I'm going to draw this table is that on this table, the first thing I'm going to express is the number of clock cycles, or the shifting number, or the shift number, okay, or number of cycles. Okay, that will be my first column. The second column will be which input bit I'm going to transmit. Okay. That is the value over here. The input bit means the value over here. Okay, that is the input bit. Next will be the content of my shift register. So means this SR1 content of my shift register means the value over here, or the value at the output that is available at the output of the SR value. This is what I meant. Okay, SR1 value over here represents the value of SR2. The value over here represents the output of SR3 that I'm drawing over here, and then this will be my B, my code B. Okay, so this is how we explain. This is how we usually explain. Then the next one, the last block I'm going to use it to explain remarks. I'm going to explain the working, or what every bit actually means. Okay, that's what I'm going to do here. So the first thing is, so you need to understand what you have to transmit. I'm going to transmit this. What was what we decided? Yes, u of x is equal to 1 plus x square plus x cube, right? So u of x is equal, let me write it, u of x is equal to 1 plus x square plus x cube, or in other words, u is equal to 1 0 1 1. So what are you going to transmit? You are going to transmit this one first, followed by this one, followed by this 0, and followed by last this one. And after transmitting all these 4 bits, then you will transmit the zeros in order to flush out the remaining answers. Okay, so in the first clock cycle, on the 0th number, before sending the clock cycle, okay, before, that is, we call it the 0th, the first position is that we don't send any cycle, we're not going to do any shifting operation, and you just simply put the bit, you just place the bit over here. So the first bit will be always, like I said before, the first bit will always be the bit of the highest order, coefficient of the highest order, which is this one over here. So first I'll transmit, or I'll put this, I'll place this one over here, and the content of the shift register, that is the output of the SR1, the output of SR2, and the output of SR3 are all zeros because no value over here, and also the output is also 0, and hence we say that the circuit is in the reset position or in the static position, reset mode. Okay, it's in the reset position because we haven't done any shifting cycle. Now how to write the values of the output is simply look at this value over here. So what is V of X? If you look at V of X, this line represents SR3. This line represents the sum of these two lines, right? So this is SR3, and this is, what is this? This is actually SR2 plus input bit. So therefore, V is equal to SR3 plus SR2 plus input bit. That is, if you want to write the output, if you want to write the output value, you need to write the value in such a way that you add SR3 plus SR2 plus the input bit. Remember that, SR3 plus SR2 plus input bit. That is the working of the circuit, okay? Specifically of this circuit, okay? So that's how we explain the circuit. So here in this case, the output is, so what happens over here in the first shift cycle, what happens over here is that first I will start from here, I will calculate the output. So what will be the output? SR3 plus SR2 plus input bit. 0 plus 0 plus 1 is 1. Okay, then what happens is that everything will be shifted. That is, this 0 will be discarded, this 0 will be shifted over here, this 0 will be shifted to the next shift register, and this 1 will be shifted over here, which means in the next clock cycle the value over here is 1, the value over here is 0, and the value over here is 0, and the value over here is 1. Okay, and also the next number is, the second bit is 1, right? So which means the next number you're going to transmit is 1. So this will be the position of the, or this will be the values at the first clock cycle. That is, this will become 1 over here. Oh, sorry, this is 0, this is SR3, this is 0, this is 1, and this is input bit is 1. That is, you place the second bit over here. This is the operation. Now at the second shift cycle, what happens is that I'm going to calculate the output. And how do I calculate the output is by simply adding these two, or by simply adding this one, and this one, or by simply adding SR3 plus SR2 plus input bit. So what is the SR3? 0. SR2 is also 0, and input bit is 1. So 0 plus 1 is also 1. This 0 will be shifted here, this 1 will be shifted here, this 1 will be shifted here, and the 0 will be shifted here. Right? Because the third bit you're going to transmit is 0, so this 0 will be shifted here. Okay, so this is how the working is. So now at the third clock cycle, I'm going to calculate the output. So what will be the output I will get? That is 0 plus 1 plus 0, 0 plus 1 plus 0, SR3 plus SR2 plus input bit, right? So 0 plus 1 plus 0, which again it is 1. Okay, and this 1 will be transmitted here, this 1 will be shifted here, and this 0 at the input bit will be shifted over here. So which means at this time and also the next bit will also enter into the circuit, will enter here. So therefore, which means that the value over here is 1, the value over here is 1, the value over here is 0, and the value over here is 1. This is the state of the circuit at the third clock cycle. Okay, so this is how it is. Okay, so next again I'm going to transmit. So what happens is that the fourth clock cycle, okay, at the fourth clock cycle, the value of V is SR1 plus SR2 plus input bit, which is 1 plus 1 plus 1. Remember, this is not a full adder or half adder or anything like that. This is pure XOR function. So what is 1 plus 1? 0. 0 plus 1 is also 1. So you'll get 1 again. Okay. And this SR2 will be shifted over to SR3. SR1 will be shifted to over here. And this input will be shifted to the over to the first shift register. And now, since you have already finished transmitting all the 4 bits, now you need to transmit all the zeros in order to flush out the remaining answers. So therefore the next input bit, now from here onwards the input bit will always be 0 only. Okay, because now now the purpose of sending zeros is to flush out the remaining answers from the shift registers. So at the next clock cycle you will get SR3 plus SR2 plus input bit, which is nothing but 1 plus 0 plus 0, which is 1. This 0 will be shifted over here, this 1 will be shifted over here, this 0 will be shifted over here, and another 0 will be similar, right? Which means that over here, this value over here is 0, the value over here is 1, the value over here is 0, and the value over here is also 0. At the 6th clock cycle, okay, first I will calculate the output. So what will be the output? SR3 plus SR2 plus input bit. 0 plus 1 plus 0 is 1, and then this 1 will be shifted over here, this 0 will be shifted over here, this 0 will be shifted over here, and then you put another 0 over here. Okay, that's what you do. Then what happens is that again at the last clock cycle, okay, at the last clock cycle, first you calculate the output, SR3 plus SR2 plus input bit, which is 1 plus 0 plus 0, which is 1. This 0 will be shifted over here, this 0 will be shifted over here, this 0 will be shifted over here. That's it. Now no need to send any more zeros because the contents of all the shift registers is all zeros. That is the first starting state. It's called as the reset mode or the starting mode. Starting mode means the contents of all the shift registers is 0, which means you have successfully flushed out all the contents of the shift registers. Okay, so when you actually look at this, okay, when you compare this operation with this operation over here, okay, like I said, when you want to express v of x in terms of its polynomial, it is written as 1 plus x square plus x cube plus x raised to 4 plus x raised to 5 plus x raised to 6, right? So which means, so you see, this is the, so the coefficient of x raised to 6 is 1, the coefficient x raised to 5 is also 1, the coefficient of x raised to 4 is 1, the coefficient of x raised to 3 is 1, the coefficient x square is 1, the coefficient of x is 1, and the coefficient of x raised to 0 is also 1. So that is what you are seeing over here exactly. Those same ones. This one represents the coefficient, I'm very short form, coefficient of x raised to 6. This one. This one represents the coefficient of x raised to 6. This one represents the coefficient of x raised to 5. This one represents the coefficient of x raised to 4. This one represents the coefficient of x raised to 3. This one represents the coefficient of x raised to 4. This one represents the coefficient of x raised to x-ray, I did make a mistake, coefficient, sorry, this is a coefficient x raised to 2, this is a coefficient x raised to 1, and this is nothing but the coefficient of x raised to 0, which means this one over here represents the coefficient of this one. This same one is this last one over here. So this is how we explain the encoding of the non-systematic cyclic code. Whereas by simply looking at the multis, all you have to do is simple. In summary of this video is that simply look at the value of the generated polynomial and draw the circuit as such. That is, if it is 1 plus x cube, which means this is 1 plus x cube. If it was 1 plus x square plus x cube, okay, I'm assuming, okay, if it was 1 plus x square plus x cube, then this will become 1 plus x square plus x cube. That means there won't be arrow mark over here. You see, so that is what I'm saying. Everything depends on the value of the multiplier coefficient or the generated polynomial. Okay, so this is how the working is. So corresponding the steps also will be different. Okay, in that case.